Today is Philip Mannheim from University of Connecticut, and he will discuss a solution to the ghost problem in higher derivative gravity.
Okay. Well, first of all, thank everyone for the kind invitation. Please bear with me. Like John Donahue, I'm coming in on two devices because one of them is a little bit shaky. Hopefully this one won't disrupt during the talk. What I've written at the bottom is the abstract to the talk that I submitted to the conference, and it's based on a paper I recently published in 2020. Okay, now we have to go all the way back to the Pauli-Villars regulator and realize that the ghost problem is 70 years old. They wanted to regularize divergences, and they proposed replacing the 1 over k squared minus m squared by a second term with a minus 1 over k squared minus m2 squared. And I'm calling this dk2 because it's meant to be a second derivative theory. They had improved convergence, which is very exciting. However, they recognized that this was only a mathematical procedure, but nonetheless, they did not want to rule out the possibility that it might be physical. As conceived, what they wanted to do was to introduce two particles, the regular one and the regulator, with a positive sign here. So these are regular kinetic energy operators. However, in order to get this regular minus sign, they explicitly introduced a ghost set of states for the 2 system with a relative minus sign here. And you insert that in this Green's function, vacuum 1, phi 1, vacuum 2, phi 2, and you recover this propagator. So they could get good asymptotic convergence, but the loss of probability and the loss of unitarity. Now, Thijs and Uhlenbeck in 1950 asked, well, whether it could be physical. So they introduced a different theory, which was a 4th order derivative theory, 4th order derivative equation of motion. And they calculated the propagator, and the propagator was exactly the same as the Pauli-Villars propagator. I've referred to it as dk4 because it's not the same as dk2. And we'll see why that's relevant in a moment. However, if you were to identify dk4 as the matrix element of T phi phi, you would still have to insert all of these states with negative norm in order to generate that minus sign. So you weren't any better off than before. However, the question is, could anything be wrong with this reasoning? It looks somewhat impeccable. And I want to show you, first of all, why something must be wrong. And it will lead us to an underlying conformal symmetry in 4th order derivative theories. Now, and let me, of course, mention that once you get into gravity, shortly after Thijs and Uhlenbeck, Kelly Stella showed that you're going to have exactly the same problems in 4th order gravity. And those problems have been with us for a long time. So let's see why something must be wrong. I just take the Dirac action coupled to geometry, where I've introduced the Vierbeins and the spin connection. And the only reason you introduce this spin connection is to make the action be locally Lorentz invariant. You didn't ask any other reason. However, it turns out that this action is also locally conformal invariant, where you change the g mu nu to e to the 2 alpha of x g mu nu, psi to minus 3 alpha of x over 2 psi, and v goes to e to the minus alpha v. So you didn't ask for it, but you got local conformal invariance for free. Moreover, if you go back to the standard 3x2x1 model, at the level of the Lagrangian, the entire theory is locally Lorentz invariant, except for the double well potential of the Higgs field. So if fermion masses could be generated dynamically, I wrote a review on this subject recently. Some of the works I've described are by participants in this conference. Then if that were the case, if masses were dynamical, the entire standard model would be locally conformal invariant. From a slightly different viewpoint, 't Hooft has also argued that there should be an underlying local conformal symmetry in nature. So what do I do with it? I look at this alpha here. I write a phase, psi goes to alpha plus I beta psi. Gauging beta is Yang-Mills. Gauging alpha is conformal gravity. And thus you can unify the standard model with gravity through the use of local real and imaginary phases. However, Conformal invariance means quadratic actions. So have we lost unitarity? Well, let's see what happens next. I take this action. I now do a path integral over the fermions, and I generate an effective action. And that effective action is the conformal gravity action. Not I, Tuhoff generated it, not me. But nonetheless, what you get is the conformal gravity action, where C is a log divergent constant. Now, why would you get the conformal gravity action? Because you're starting off with a conformal invariant theory, and you're doing a path integral over the fermions. However, we now have to ask, well, is there a ghost here? Well, we started out with a Dirac action, which is the standard model, and the standard model is ghost-free. So there was no ghost before we did the fermion integration, but a path integral over the fermions is equivalent to a one-loop Feynman diagram. And you can't change the signature of a Hilbert space in perturbation theory. So conformal gravity must be ghost-free. Now, suppose it were not. Then the standard model couldn't have been unitary either, because as soon as you integrate it out in the presence of an external gravitational field, you would immediately hit the ghost. So radiative corrections to the standard model in an external gravitational field generate the fourth order theory whether you like it or not. So we have to deal with it one way or the other. So where could things possibly go wrong? Well, the propagator that we wrote down, the dk4 with the relative minus sign, is a C number. And when you have a C number, you can't automatically identify it with any particular Q number before you first construct the quantum theory. You can construct C numbers from Q numbers, but not vice versa. Secondly, just because the second order Pauli-Villars is associated with the loss of unitarity, it does not mean that the fourth order one is too. In order to find out, you need to construct the quantum Hilbert space first. So that's where things could go wrong. So where do things go wrong? Carl Bender and I discussed this point, and we constructed the Hilbert space, and we found the following. You define a right eigenvacuum, which obeys H omega right is 0. A left eigenvacuum obeys omega left H equals 0. Is the left eigenvacuum the Hermitian conjugate of the right eigenvacuum? Answer, yes, only if the Hamiltonian is Hermitian. Well, is it Hermitian? Well, that depends on boundary conditions. Boundary conditions are such that the Hamiltonian of these fourth order theories is not Hermitian, which means you cannot integrate by parts. But it does turn out to still be CPT symmetric, and omega left is the CPT conjugate of omega right, not the Hermitian conjugate. Now, in gravity, C is all separately conserved because the gravitational field is C even, and so CP symmetry defaults to PT symmetry. And so this theory falls into the class of PT symmetry theories, which were initiated by Carl Bender. However, even though the Hamiltonian is not Hermitian, all the poles of TK4 are on the real axis. Let's just look at it. All the poles are on the real axis. So whatever happens, we know that all the eigenvalues, energy eigenvalues are real. That can't change. But we have a theory which is not Hermitian, but nonetheless has real eigenvalues, and that's exactly what these PT theories are. Hermiticity is only sufficient to give real eigenvalues. CPT symmetry is necessary. As regards causality, we can comment the following. This propagator here and this propagator here have the standard I epsilon Feynman prescription. Both of them are independently causal if you integrate over the standard Feynman contour. Putting in the minus sign does not change the causal properties of this propagator, and so the theory is also causal. There is a question, well, what happens if you make the masses into a complex conjugate pair, and that gets you into Lee-Wick. But as far as if I stay where I am with real masses, the theory is causal. So the propagator that we're looking for is not omega right T phi phi omega right, it's omega left T phi phi omega right. And the left right inner product is positive definite, that I'm going to show you in a few moments. Now, because of the boundary conditions, you can't use this relation, the thing that you would like to, you fear you may have to use, because these states are not normalizable. And so this completeness relation is not valid. So now let's go to the proof. So that's what must happen. Now, the only thing you ever care about for quantization is time derivatives. I said omega 1 is k squared plus m1, omega 2 k squared plus m2 squared. And this action that I had started with for the scalar field, which is also the same action as you've got second order plus fourth order gravity, it's exactly the same action, reduces to what's called the Pais-Uhlenbeck action. Now, the Pais-Uhlenbeck action contains the z double dot squared, the z dot squared, and the z squared. And now we count variables. We've got a z dot, and a z double dot. That's too many variables for one oscillator, but not enough for two. So what you have to do is you set z dot is equal to x, and you can use the method of Ostrogrodsky, or you can use the method of Dirac constraints, and you will finish up with this Hamiltonian. This Hamiltonian is the Hamiltonian of this action, and z and pz are the things we started with. They're a canonical pair. X and its conjugate is also a second canonical pair. Now you look at this action and you see immediately, here's the minus z squared, and that's the Ostrogrodsky instability. So that's something we're going to have to take care of. Okay. Now, Lee and Chellan and Pauli and Heisenberg realized that you could trade away the Ostrogrodsky singularity by having negative norm state to see how that is. I just introduced z, pz, x, and px. I introduced two sets of oscillators, A1 and A2. I calculate the Hamiltonian, and I calculate the commutators, and you see there are two minus signs. One relative minus sign in the Hamiltonian, and one minus sign in the commutator. So you have two choices. If you take A2 to annihilate the vacuum, then you have negative energies. Sorry, if you take A2 dagger to annihilate the vacuum, then A2 dagger becomes the annihilator, and the annihilator times the creator becomes positive, and now you have no problem with negative norms, but now you've got a problem with negative energies. On the other hand, if you say, I'm going to take A2 to annihilate the vacuum, that minus sign turns this piece into positive energy, but at the price of negative norms. So you have two choices. A2 annihilates the vacuum, you have negative norms. A2 dagger annihilates the vacuum, you have negative energies, but they are different Hilbert spaces. They don't occur in the same Hilbert space. You can have one or the other, but you don't have to deal with both. But you still have to deal with them. So we've seen there are two possibilities. I just mentioned them. I just state again. A1 and A2 annihilate the vacuum, or A1 and A2 dagger annihilate the vacuum. Now, if A2 dagger annihilates the vacuum, then you've got negative energy states propagating forward in time, which means the energy spectrum is unbounded from below. But nonetheless, remember, all the energy eigenvalues are still real. So what we can do now is we can take this Hamiltonian and we can solve the Schrodinger problem. We take the commutator, we set Pz is minus id by dz, Px is minus id by dx, and look for the solutions to the wave equation. And you can find them very quickly. And here's the one of lowest omega 1 plus omega 2. And you notice that while it's minus x squared, over here it's plus z squared. This state is not normalizable. So if I calculate the vacuum, integral dx dz, put in the complete set of states, psi star psi, it's infinite. This is not a normalizable state. If you wanted to consider the other possibility that you looked at the negative energies, you would find they weren't normalizable either. So none of the wave functions of the theory are normalizable. But since they're not normalizable, you can't use this relationship. You can't use the standard closure relationship. However, We still have to deal with the fact that things are not normalizable. However, rather than being a bad thing, it's the lack of normalizability that actually saves the theory. So let's see, how do we make this thing normalizable? Well, first of all, by the way, if it's not normalizable, then it meant I could not integrate by parts, and therefore the Hamiltonian on those states is not Hermitian, which is what I was claiming at the beginning. How do you make it normalizable? You have to continue Z into the complex plane. And so what you do is, if you imagine a letter X, you are in the complex region, namely the upper and the lower, the north and the south quadrants, not in the east and the west quadrants. These are called Stokes wedges. These wave functions are normalizable in the complex plane. So how do you implement that fact? You simply make a similarity transformation. Y is this similarity transform is minus IZ. Q is IPZ. This is a canonical transformation. Y and Q obey the canonical commutation relations. And the Hamiltonian, and this was the important point. Remember that we have here the PZ times X, and that will cause us to get here a complex I. So under this similarity transformation, we now have a Hamiltonian that's manifestly not Hermitian, but it's Schrodinger problem. All of its eigenstates are well behaved. And this is a classic example of what's called PT. This Hamiltonian has a PT symmetry. X and Y are PT odd, P and Q are PT even. Once you've specified how X and Y behave, P and Q are fixed by the commutation relations, and PT symmetry allows for energy eigenvalues to be real, even without hermiticity. Now you ask the following question: how on earth could Z not be Hermitian? I mean, after all, the whole argument that we deal with all the time, where if I can find it, oh, I'm sorry, I went too far. The whole argument is that this term is negative because we're taking it as a given that Z is Hermitian, because we have the usual classical analog in the back of our minds. But I've shown you that it's not Hermitian. So now the question is, how could it not be Hermitian? Well, any operator that obeys a canonical commutation relation is Hermitian when it acts on its own eigenstates. But that does not make it Hermitian when it acts on the eigenstates of some other operator, such as the Hamiltonian. And that's the secret of PT theory. You need to construct the eigenstates of the Hamiltonian and not the eigenstates of the operators in the Hamiltonian. And that's the difference. And that's why you could have a well-behaved Hamiltonian with objects that look like they are not, look like they should have been Hermitian. And of course, if Z goes to IY, then that minus Z squared now becomes plus Y squared. But still, we have another problem. So now we've got rid of the Ostrogodsky, but have we got rid of the ghost? So I have to make one more transformation. I introduce an operator Q as alpha px, Q, beta xy. This is the function alpha, and I apply it to the Hamiltonian we just obtained, and I obtain P squared plus Q squared plus X squared plus Y squared. So this is a completely normal two-particle Hamiltonian, two-dimensional oscillator. And all I've done in the end, I've just made two similarity transformations, similarity 1 and similarity 2. Now, when you do a similarity transformation, you can't change the energy eigenvalues. You can change the wave functions, but not the energies. And so, again, we finish up with everybody real. And now these operators are all Hermitian. So what has really happened is that the theory that we started with, is actually Hermitian in disguise. After you make a transformation on it, you will finish up in a Hermitian basis. And the reason that you will have to be careful is because the operator Q is not unitary. The operator e to the q is not unitary. It's a transformation from a skew basis to an orthogonal basis. Now you can construct the eigenstates of H prime, and they're just standard delta functions, but they are related to the original states of the H bar, I'm sorry. And what we find is that because n prime is a delta function, n e to the minus qm is also a delta function, and that's the norm. That's the scalar product of the theory. And so what we find is that the states that matter are not the right eigenvector and its conjugate, but the right eigenvector and the left eigenvector. And so the overlap of the right eigenvector and the left eigenvector gives you a completely well-behaved theory, and you get a regular completeness relation. And this says right left equals I, and that means that the S matrix is not right. The S matrix is right left. So that's the trick. So where did the minus sign go? Well, the answer is the matrix element is right vacuum, left vacuum, and that picks up this e to the minus q. And that means that when you put in intermediate states, it's not a modular squared. And when you calculate it through with the positive frequency, with the positive closure relationship, you still get, you generate the minus sign in a theory with a positive definite metric and no negative norm states, and of course, no negative energy states. So the mistake was in thinking that you could write before you did the calculation that you already knew this was going to be the Green's function. And the answer is no, you have to work it out to see exactly what it is. Now, what happens in loops? So if I write a propagator, then I'm going to have here a plus and a minus, and I'm going to have here a plus and a minus, and I'm going to have overlaps between a plus contribution in the upper line and a minus contribution in the lower line. And then if I calculate the discontinuity across that graph, it's going to be negative. That on its own is going to violate unitarity. However, there's more to the theory than this graph. In the same way that I made these similarity transformations to bring the Hamiltonian to a diagonal form, the interaction, lambda phi to the 4, becomes a very complicated quantity. And what happens is the tree graph gets modified, the vertices get modified, and the sum of the graphs is unitary. Damiano Anselmi has also talked about modifications of the tree graph. So that's what happens in loops. Now, why must it happen? Because once I've quantized the theory, in perturbation theory, I can't change the signature of the Hilbert space. So I must stay in a positive norm space, but it just doesn't appear that way until you start combining and calculating the S matrix. Okay, so that's how the theory works. So now for my summary, the discussion questions. Renormalizability, well, that's fourth order, that's okay. Unitarity, positive energies, locality, causality, the locality, the commutators vanish for space-like separated points. Can we live with all of that? The answer is yes, if you identify the Hilbert space correctly. Should the correspondence principle still be valid in the quantum theory of gravity? Yes, but you have to do what I just did. You have to make this rotation, wherever it is, you have to make that rotation in the complex plane. So you make a similarity transformation in the quantum theory and a symplectic transformation in the classical theory, and then you can have a correspondence principle. It's just not on the real axis. Can gross be made harmless in the quantum theory? Yes, and the Ostrogorsky theorem is taken care of at the same level. Can a consistent quantum theory of gravity avoid strong coupling? The answer is that there's no need. It's a consistent theory at all couplings. Can we rule out the possibility that general relativity is non-perturbatively renormalizable or even finite? We certainly can't rule it out. But what we can find is that the fourth order theory is renormalizable. And there is a possibility that it's finite if we're at a fixed point, but that's still not resolved. Are higher order derivatives necessary? And the answer is yes. Not only are they necessary, they're unavoidable. Okay. So should matter be necessarily taken into account to formulate a consistent quantum theory of gravity? Yes. I didn't discuss that at all. But when you try to work this through, what you discover is that gravity has to be intrinsically quantum mechanical. In other words, gravity is quantized by its coupling to quantum matter, and classical gravity is output when you calculate physics in states with an indefinite number of operators in an indefinite number of gravitons. But yes, you have to absolutely take quantum mechanics into account. Okay, so the other points are points I haven't addressed, but we'll address them, I hope, during the conference. Thank you.
Thanks, Philip, for this nice talk. Are there questions? Richard, you have to mute yourself.
Unmute, Richard has it.
I'm unmuted. I got kind of lost during the first part where you were talking about integrating out fermion fields, and you seem to get a local effective action from doing that. How did that happen?
Oh, that's just what you get. I mean, it's what you're thinking about is integrating out other theories, but this is a straight calculation. You just do the path integral, and that's what you get.
I don't understand that. It seems to me
okay,
that
I think what you're thinking about, perhaps I think what you're thinking about is this. If I had added onto this action sources, J psi bar and J bar psi, then I would have generated a J bar delta function, a delta propagator J term as well.
You're doing it in the presence of a background metric. Surely you must
doing it in the presence. Absolutely, yes.
Surely you have to get the conformal anomaly term, which is going to be something like C log box C. How can you avoid that?
Okay, I've announced that I got this term. Now, I didn't say that I don't get anything else. I just said that I do get this term. Now, you're asking a different question.
Well, you have an equal sign there.
Well, you're asking me what else do I get? That's a different question. I wanted to show you what I do get. What I don't get, by the way, is the Einstein-Hilbert action. I wanted to show you why this term occurs. Now,
it's okay. So you mean plus ... right?
No, sure. There's more.
Oh, okay, so
I just said.
Fair enough. That answers my question.
Okay, but however, you have raised an important question. There is an anomaly, and when you work it through, there is an anomaly in the gravity side, and there's an anomaly in the matter side. And the way that the theory is quantized, they cancel each other. That's the new piece about, once you've got quantum gravity, you have a new, once you've got a consistent quantum theory, you've got something new. And that's this. When you look at the matter loops will generate you an anomaly. However, you can't cancel it by gravity unless gravity itself is quantized and you can calculate gravity loops. And when you work this theory through, and I've published it already, the gravity loop and the matter loops cancel each other. And there's no net anomaly.
Next, there is a question by Tubulis. You have to mute yourself.
Okay. Yeah, going back to exactly this question, equation 11, you get, of course, the extra stuff, which will be log terms, non-local terms from integrating out the loops.
Yes.
That creates two effects. First of all, if you include matter, let's say n matter fields, it'll be proportional to n. Yes. So the matter corrections dominate. You cannot cancel everything by the single gravitational loop. In fact, that's the basis of the 1/n expansion, which I was involved years and years ago. Very nice expansion in higher derivative theory that it's unitary at the leading order in 1/n, precisely because there is another point that I think it's a problem with what you said. that once you do these corrections with these extra non-local terms, and you look at the poles, the would-be ghosts move into the complex plane. You cannot, once you do quantum corrections, the zeros in the denominator of the propagator are no longer real. They move into the complex plane, and you get complex conjugate pairs.
Yes.
That allows you to have unitarity to leading ordering 1 over n. But the question is what happens to higher orders? And that's too complicated. As far as I know, nobody has ever been able to answer that question.
Okay, I have to make
okay.
2 comments. Comment number 1. The way that this theory quantizes, you've got a statement which says gravity equals matter. If you have n sources in the matter side, the wave function renormalization of the gravity side will be proportional to n. It's not something that you can assign independently. And that's the difference. That's why I said when John was speaking that I don't quantize gravity canonically at all. Gravity is quantized by whatever source it has. Now, the second comment is...
Sorry, not canonical quantization, just path integral, straightforward integration.
Yeah, no, I'm saying is that when I do quantize the theory, which I've done, the graviton wave function renormalization constant is proportional to how many fermions or how many particles there are in the theory. It's not determined by gravity alone. The way I do things, gravity doesn't exist on its own. I can explain that if you want, but I wanted to go back to something else you said first. Where is it? In PT symmetry, if you have a Hamiltonian has an antilinear symmetry, then the energies are either real or in complex conjugate pairs. So what you've described about the complex conjugate pair moving into the complex plane is completely compatible with antilinear symmetry. In other words, CPT allows that to occur. CPT does not require energies to be real. It requires energies real or energies in complex conjugate pairs. So yes, so that's a perfectly reasonable occurrence in a PT theory, which this theory is.
So why did you say that at the beginning that you made a point about the poles being real?
Oh, no, I started out with this. I'm trying to address, Carl and I were trying to be very straightforward. We were trying to address this particular propagator. And this particular propagator, all the poles are real. I mean, that's the one we were trying to solve. Now, if you have m1 squared plus I gamma and m2 squared minus I gamma appearing, then you will still have an underlying PT structure. And we've discussed how this extends to the Lee-Wick situation. But what I said at the beginning was simply I'm looking at this particular propagator, and that's the one I wanted to address. But you're right, it leads me into a whole different world, because once I'm in the PT world, then I have this possibility of complex conjugate pairs.
Okay, so I think this is a good point to close this discussion. So let's thank Philip again. And okay, I would suggest that now we have 10 minutes of break, and then we